Hello and welcome to an ad hoc talk on the state of play for Power ISA simulators. The first thing to be aware is that Power ISA has been around since 1994-93, has gone through a lot of revisions. Initially started off as 32-bit only, was used in Macintosh products, and then it sort of grew from there in IBM. It took it, to 64-bit, added, basically turned it into a supercomputing ISA. You have to be aware of this because the number of emulators that actually exist is really quite large. It's just that they haven't really been kept up to date. At least the open source ones. So there's quite a lot of history to cover in this. So this is a list of ones that I've been able to find. It includes a one by IBM, which is proprietary. Then there's Gem 5, which is very well known amongst academic in academic circles. There's QEMU, which has a PowerPC 32-bit and 64 thing, and then there's a whole stack of 32-bit only ones, including Dolphin PC, Pear PC, and a beautiful one called Sheep Shaver. Which all of these are 32-bit. Now, Dolphin PC is focused on 32-bit power emulation for Nintendo game consoles. So the Wii was Wii, the original one was actually using a PowerPC processor. Sheep Shaver is actually on its website. It's for emulation of the Mac operating systems, which were available for G4 and G5 processors. So you actually have to have that operating system a copy of that operating system from 15 years ago, a license for it, in order to run it, but it will actually work. So my favorite one is PSIM. I didn't realize that in GDB, GNU Debugger, there is actually an emulator, a Power ISA emulator. I believe that one is also 32-bit. So I'm presenting a bit of a conundrum if you want to actually do development, and simulation. Is IBM's one. Let's have a look at that one. Let's go through them first. And we'll go over the features that each has in a comparative table later. Once we've done had a look at what they have, what each of them have. So this is the IBM one. They've updated it to Power 10. It basically implements what IBM has implemented, so although it is fully feature complete, as far as Power 8, Power 9, and Power 10 are concerned, it's proprietary. You should have absolutely no expectation of being able to modify the source code for any kind of academic work. Right? If you want to actually emulate and simulate existing binaries compatible with the Power ISA, no problem. Right? The source code is not available, and there's a very specific reason for that. It's because IBM uses this internally for their own benefit for their power products, their proprietary power products. Right? Consequently, it has things like, in the source code, it will have things like, this is really complicated. It's a new instruction which hasn't been submitted to the Open Power ISA working group yet. Please contact this internal directory of IBM confidential employees list to phone up and find out what this is about. Releasing that information would not be in IBM's interest. Neither the confidentiality of the instructions that they're planning to add, nor the internal IBM directory telephone numbers. So we have asked, and they've just said no, we're not. You're not having the source code. Nobody is, and that's perfectly reasonable for them to do because it's for the benefit of their products. All right. So that's that one. Now, it is the thing about it, the IBM simulator, it is of all of the simulated, it will be the most feature complete of the entire lot. So if you absolutely want absolute compatibility with everything that the Power ISA has to offer, you want that one. Okay. Now, Gem 5. Gem 5 is quite an interesting one because it has a whole stack of other ISAs. It's the one that's most well known in academia, supporting MIPS, RISC-V, x86, ARM, you name it, thing. And there are dozens of academic papers, publications. Go to publications. There's a list here, thing. And I mean, just holy cow. Publications using Gem 5, 2017, 16, 15, sort of thing, about 2002. People are creating GPUs on it. They're doing estimations of power consumption on DRAM controllers. And one of the reasons for that is because Gem 5 very specifically focuses on cycle accurate simulation, and by that I mean that hardware cycle accurate simulation. All right, there's a difference between that and program order accurate. So basically, it emulates. It doesn't just emulate an instruction set. It emulates the level 1 and level 2 caches, and the time that is taken for instructions to complete and instructions to load, and the speed of the memory controller. So you can get statistical information about the performance of your program and also the addition of whatever instructions for a particular architecture. All right, so if you have an in-order system, you can get the performance of how your program will operate on an in-order core. If you have an out-of-order system or a multi-issue, etc., etc. Now, there are all of these things. Somebody has to actually implement them, right? And for some architectures, there is a whole wealth of things, but for Power ISA, it's fairly limited, right? So somebody has to do the work, right? Now, progress on Gem 5 is it's quite interesting. Again, I did say there was quite a lot of history there. There's a branch called Gem 5 Experimental, which started 3 years ago, which was sponsored by IBM, and was the result of some IBM interns adding features to Gem 5, the power port. As prior to their work, Gem 5 was only supported 32-bit instructions and 32-bit scalar instructions, big endian, and that's about it. So it was absolutely fantastic work. Basically, what the students did was they added a Radix MMU, they implemented the ZIX interrupt controller. They added a basic peripheral support for serial console, and they also added 64-bit scalar instructions, just the integer ones, and that, fascinatingly, was enough. Oh, and they also added bare metal boot. So fascinatingly, that was enough to be able to do a full boot of build root to BusyBox prompt. Absolutely brilliant. It was a lot of work, and Sandepan Das, myself, Jason Lowe, and Boris Shingarov worked for about 6 weeks to extract the 64-bit work and get it upstream. But that still left the Radix MMU, the ZIX controller, and the bare metal ability to think. Now, just to explain some terminology there, you've got on any emulator you have a host, and the host can be any processor. It can be x86, it could be ARM, it could be MIPS, it could be anything. And then you have the guest, and the guest can be anything. In this case, we're talking about PowerISA. So you can have on an x86 system, you can emulate PowerPC, all right, PowerISA, right? So we call that the host will be the actual hardware that you are running the emulator program on, and the guest will be the guest instruction set, which has nothing to do with the host at all, right? Under that guest, you can have user space programs, or you can have bare metal programs where you actually run full operating systems, okay? And they're radically different, okay? They're completely different requirements. And the kicker, the key thing that makes the difference there is memory management and virtual memory, because that is it results in horrendous performance. I'll explain that later in a bit. So coming back to this Gen 5 experimental branch, we extracted Jason Lowe, myself, Sandepan, and Boris extracted the 64-bit instructions, of which there were a lot added by this IBM interns thing, and brought it basically up to date. But what we didn't have time to do was to do the Radix MMU, the ZIX interrupt controller, and the ability for the guest operating system to run bare metal operating systems. So you can only, at the moment, the current mainline Gem 5 can only run, where you can run 32-bit or 64-bit user space binaries only. It cannot run a full operating system. Somebody will have to extract the work and the remaining work from the Power Gem 5 branch, Gem 5 experimental branch. Now there is also some work by Virginia Tech. I must apologize. I've heard about this. Unfortunately, I don't know at the time of writing. We may find out during the talk, which this is being planned 24 hours in advance. We may find out where that is and be able to refer to it. But Virginia Tech has added some of the SIMD instructions. As part of Virginia Tech intern and master's and PhD work, and they're also planning to add floating point, scalar floating point. I'll do a little bit about that, especially at the end as well. Now, In addition to that, what's absolutely fantastic is that we've learned that the IBM India research is planning another round of internship to extend Gem 5 even further, which is absolutely fantastic. So really wish them all the best with that. And basically what it means is that, if you're a student in India, you'll be able to get you'll be able to work as an intern at IBM. It's absolutely great. Now, there's also QEMU. The lovely QEMU. All right. QEMU again. It's a full system emulator. Also capable of running user mode as well. And supports pretty much everything. Like Gem 5, it pretty much supports everything. The thing is, the difference between Gem 5 and QEMU is that QEMU is not a hardware cycle accurate simulator. It does just-in-time binary translation. So to illustrate that, if you have something that you need to debug within the guest, and you want to single step over an instruction, you will not be single stepping through the actual instruction in QEMU. You will be single stepping through a series of just-in-time binary translated emulated equivalents to that power ISA instruction. That's radically different, and it means unlike in Gem 5, the instructions are written. They're actually written in C, C++, and also pseudocode. It's completely different. Sort of in environment. QEMU, there isn't necessarily the one-to-one relation. Basically, what I'm saying is there isn't the one-to-one relationship between the guest instruction being emulated and what actually happens under the hood in the QEMU emulator. All right. The other thing about Q, this is probably good as time anyway to raise it. Let's do the other ones first before we go to that. Now, Dolphin PC and Pear PC and Sheepshaver, these are all 32-bit. They're very old. They work. They're of historical interest to people who have emulators and to retro games consoles and retro operating systems and retro this, that, and the other. All right, they're brilliant, but it's for modern research purposes. Nah. All right. Of special note is KavaTools. KavaTools, which is developed by Peter Hsu, is absolutely fantastic. It's phenomenal. It's very, very specific. The first notable thing is that it is the only one of the emulators that the more cores you have, the more you can dedicate. They are all parallel. It's a parallel processing system. So on your host, if you have multiple cores, performance is directly proportional to the number of cores on the host. Whereas all of the other emulators, if you have a symmetric multiprocessing operating system that you want to emulate and it has 64 cores, then you get one thread allocated to all 64 cores, emulated cores and performance tanks to 1/64th of what it would be on a native hardware, whereas Carvatools is specifically designed to be multi-threaded. So if you have a 64 core system and you emulate a 64 core SMP program, performance remains 1-to-1. All right, that's very, very different, and it's best to watch the ICS International Supercomputing Conference 2021 talk, because the reason for Peter did that was that if you are attempting to develop something where you have a program which is real-time number crunching and interactive, and the program is multi-threaded, you really seriously need to be able to emulate that the program in real time. You want the emulator, you want the users to be able to interact with your emulated program in real time, right? And if it's a particularly computationally high performance one, the last thing you need is for the emulated program to run at 64 times slower, just because only one of the host cores is capable of running the 64 SMP threads. All right. The caveat of Carvatools is that it is user space only. It gets its performance by not tackling virtual memory, right? So you have to compile a user space program and run it under Carvatools. It will not emulate an operating system, right? And for most programs, that's perfectly fine. You know, if you have a specific focus on high performance applications, you want to do a 3D graphics thing, or you want to do real-time image processing to present the images to the user. You don't want to emulate a full operating system. You just want to emulate the damn program. So that's what that's about. Then there's the one but LibreSoc team, which is the team I'm associated with, which we called ISACaller, because it's an ISA. You call the instructions. I have absolutely no ability to name things in any sensible fashion. Now the thing about this, about ISACaller, is it's very specifically designed to be as close to the Power ISA specification as it is humanly possible to be. So what we've done is we've taken the actual specification directly out of the Power ISA PDF. We have literally taken the pseudocode out of the specification and made it executable. Right? We've done that through a compiler. Right? It just sup.org/open power/ISA. Okay. Snooze. Okay, all right, so let's go to fixed arithmetic. Anyone who is familiar with the Power ISA specification, the PDF Power ISA Public v3.0 or v3.1, will immediately recognize this source code, this code. And what we've done is we've literally made that translate into Python. You directly execute that pseudocode. And what that means is that as far as development is concerned, we can provide, we found bugs in the Power ISA pseudocode specification and reported them to the Open Power Foundation for corrections. We found ambiguities. We've also had to do a number of corrections, and one of the most interesting ones I think is overflow. To properly implement the multiply mul LW, we had to add this overflow detection flag to the thing, because if you have a look at the ISA specification, it says it just has these two lines, and then in English language it says how to detect overflow, but there's no actual source code and no specification notes in pseudocode form telling you how to do the overflow. So we had to write it and then write a whole stack of unit tests checking the damn thing. All right. So the ISA caller goes right down to literal, I'm not kidding, to bit level emulation. Right, but also it does that bit level emulation in IBM MSB0 order. Most significant is numbered 0 in the IBM Power in the Power, so Open Power ISA specification. Right, the normal convention that you will encounter numbering everywhere else except for Power ISA is the LSB0 order. So the least significant bit is numbered 0. Right? And Power ISA, it's 1. So this here is 0 here is the highest bit, not the lowest bit. Okay, it's critically important to appreciate. And everybody else who does these emulators and simulators and etc., what they do is they go, oh, let's look at that and let's translate it into LSB from MSB to 0. So you have to do 63 minus thing. If it's a 64-bit number, you have to subtract all the numbers. 63 minus this. If it's a 32-bit number, you have to do 31 minus this to convert from the Power ISA spec, and you can make mistakes. So we decided that that's not acceptable, and wrote a Python class called selectable int, which does that translation automatically for you. Right? So you cannot make mistakes. And what it means is that you can actually write with ISA caller. You can develop actual pseudocode which you're going to propose to the Open Power Foundation through the ISA working group, and actually test it out and have it executed and make sure that it actually passes. So that's the primary purpose of a primary process. It's completely different. Now the penalty for this is that the speed of execution is a measly 2,500 instructions a second, and that's on really fast hardware. Most mid-end laptops, we've had people saying, yeah, I can only get about 250, and to be honest, we don't care, because what this is doing is it is comparing against HDL, and the HDL is horribly slow to emulate. So if you've got something that's doing 10 instructions per second, 2,500, because your HDL emulator, you're doing gate level emulation, 2,500 instructions a second is 250 times faster than that, and it's pretty damn good. Now, the other thing about I'm trying to find the tab. The other thing about ISA caller is that we also emulate the Radix MMU. So that's really quite unusual. There's only 3 emulators that emulate the Radix MMU, and those are the Gem 5 experimental branch, not the mainline Gem 5 yet, because that, again, as I said, that has to be ported, has to be brought forward and submitted for review. So the Gem 5 experimental, QEMU, and the ineptly named Isocaller. And in the development of that, in the development of this code, the MMU, where is it? Radix MMU. Here we go. We basically looked at Microwatt HDL source code, QEMU's implementation of Radix MMU, and the Gem 5 experimental. And you will see, if you have a look at the Gem 5 experimental, you will see that these tables and the examples are directly out of the Gem 5 experimental source code. So the whole idea of this is to make readable code that's obvious, documented, you can understand what's going on. This is the benefit of Isocaller and it being in Python, and you can relate it directly to the specification, right? Because it's much harder when you've translated something to C++, and so on. But yeah, this came from the all of this work came from both Microwatt and the Gem 5 experimental branches. So yeah, unit tests, as you would expect. So you can actually, there's a standalone program you can run these unit tests and learn about and find out about how the Power ISA Radix MMU works. So let's come back then to this comparison of this table and see what they've got. See what it is. Okay, so cycle accurate hardware cycle accurate. I don't think that the IBM one is. So I'm going to put no on that one. Cycle accuracy, IBM would say it's basically it's Gem 5, Gem 5 and Carver Tools, right? Because that's Carver Tools is specifically designed to allow you to add new instructions, experiment, and see how they what effect the thing is. You know, in your hot loop, are you missing things? And what's really nice about Carver Tools is you can have it's got a real-time console where you can you can have a look at the execution execution log and see, in this hot loop right now in real time, it's only running, there's a stall in this loop because floating point is taking too long, number of cycles, blah blah blah. But it's like Gem 5, the only machine that it is cycle accurate to at the moment is an in-order machine, in-order single issue machine, right? Whereas Gem 5 itself has in place in other ISAs, not in Power, it has the out of order and multi-issue, etc., and different microarchitectures. So somebody has to do the work to put all these things in. All right. QEMU is not cycle accurate. None of the 32-bit emulators are accurate, and Isocaller are in no way a thing. I mean, we'd end up with the performance absolutely sucking more than it already does. The speed of these emulators, IBM one, honestly, I don't know. It's proprietary. I've never run it. Gem 5, I really don't know, but because okay, I'll come on to a bit about MMUs after I've gone down this column. I would estimate it's probably going to be about 20,000 instructions per second, but honestly I don't know. QEMU, because it's a just-in-time emulator, I would expect to be of the order of 100k. Carver Tools, absolutely phenomenal. It's 300 on a per core. Bear in mind this is per host core on a lowly 3 gigahertz laptop. You can get 1/10 of the 10% of the native host system per core. No other simulator does that, right? And Isacaller, 2,500 instructions per second. Yes. All right. So I put SMP in this column, but I don't honestly know if the IBM simulator, if you have more cores and the host, if it will speed things up. Gem 5, no, definitely not. QEMU, no. Dolphin PC and all of the other simulators, almost certainly not. Carver Tools, yes. Carver Tools is basically the only one that I know for sure has this multi-threading scalability. Right, now that's completely different from the guest operating system. Right, the IBM simulator will be capable of emulating multi-core guests. Gem 5 should be capable of emulating multi-core guests operating systems. QEMU definitely can emulate symmetric multiprocessing guests. Dolphin PC, no. Carver Tools, because it's user space, yes, it definitely can. Isacaller, nah. Memory usage. The IBM simulator, I honestly don't know how much it is. Gem 5 is absolutely mental. The size of the executable binaries without debug information are a gigabyte in size. That is completely nuts. So just the executable. And Sandipan very kindly helped track down and fix a bug in the Gem 5 experimental branch where my laptop was starting to fall over, and we found that it was leaking 500 megabytes a second of memory. Very fortunately we fixed that, so it is actually stable, but because it's split C++ and it's auto-generated C++ classes, it's very easy to end up with insane amounts of memory being allocated. QEMU will be reasonable. It's just-in-time emulation. Resources will be reasonably efficient, but don't expect staggering performance. 1/20th to 1/30th of thing. People have installed operating systems under QEMU, and it takes several hours. To install, unless you're actually running on native hardware. The thing about QEMU is there is actually KVM mode, where hypervisor mode, where you can actually run, if you are running QEMU on native Power ISA hardware, which basically means Power 9, it can directly execute those instructions natively. So the guest operating system, that's the point of KVM, the guest operating system ends up with the guest instructions being executed natively by the host. They're not emulated. But obviously if you try that on an x86, it ain't going to work, because an x86 host isn't capable of executing natively Power ISA instructions. All right. So memory usage on QEMU will be okay. Dolphin PC, honestly, I don't know. I would expect it to be reasonable. Carver Tools would be very good. Again, a thing. And Isacaller, it's Python. Go figure. All right. So 32-bit. All of these simulators will run 32-bit instructions. 64-bit is, however, a different matter. Up until 3 years ago, this line for Gen 5 would have been 64-bit, would have been no. But thanks to Sandipan and Boris and Jason Low Powers, Jason Low and my work, that's now upstream. It does actually do 64-bit. Dolphin PC and some of the other ones like Sheepshaver and Pear PC, those are all 32-bit. The Carver tools, bear in mind, there's an NLNAT grant which I'm responsible for allocating. We're going. The answer to this will be yes. We will be doing 64-bit. Isocaller again, yes, it will do 64-bit. Floating point, IBM Simulator, I would expect them to do floating point perfectly well. Now, Gen 5, no. This is where it gets interesting. So IEEE floating point is a series of it's supposed to be a standard, but it isn't. Soft floats. Now, this is Berkeley soft float. The problem with floating point comes as far as the normalization is concerned. Rounding modes, not a number, whether it's quiet nan or signaling nan, not a number, and exceptions. There's the IEEE 7554 specification, which unfortunately is an ITU style standard, SCI. It means it's a one-way push as far as we're concerned. You can't even get the damn spec. You have to have a confidentiality agreement with your university, and then you can't actually do anything, publish it. It's ridiculous. It's the fundamental basis of computer science, and we can't even see what the damn floating point number specification is. Although the calculations of computation of numbers, adding, etc., is well specified, when it comes to the rounding modes and also to signaling numbers and nans and exceptions, that is down to implementations. So the way that RISC-V handles signaling, not a number, is completely different from the way that ARM handles it. Is completely different from the way that x86 handles it. Is completely different way from the way that Power ISA handles it. Which means the upshot of this is that when you want to emulate IEEE 754, and you have a program which specifically relies on some rounding effects occurring, the behavior of your program when it is emulated will not be the same as if you were running it on the host native hardware. Right? And the only way to fix that is to have a software implementation for your ISA. And that is what Berkeley SoftFloat is. So on a x86 system, you can get full compliance with ARM IEEE 754 weirdities. And likewise on a MIPS architecture, you can get full binary bit level compatibility with x86, including full exceptions. Now, because Power ISA has been such a well-kept secret, and because basically because Apple went with x86 12 years ago now, there has not been the focus on Power ISA, and so consequently as much of a focus on it outside of IBM, and consequently SoftFloat does not have support for bit level binary compatibility with the Power version of IEEE 754. Consequently, what you will see in, for example, in QEMU, is that although they support floating point, if there is a rounding thing, if you compile QEMU on x86 and you set one of the rounding flags for Power ISA special modes, it gets completely ignored. And exceptions will not work properly either. That's on QEMU, and if floating point is added to Gem 5, you will have exactly the same problem. Right? ISA caller, we have added some floating point numbers, but we have to add a full floating point and normalization, etc., at some point, because we're using it to as a verification system against the HDL, the LibreSoc HDL. Right, so we have to have full bit level interoperability, and because we're only doing 2,500 instructions a second, that's perfectly fine if we do even bit level emulation of IEEE 754. Right, so it's quite a lot to think about amongst these emulators of what you to do. Now, SIMD. Bear in mind, VSX is not a vector extension. It is a packed SIMD extension. Please do not make the mistake of thinking that just because VSX has the word vector in it, that it is a vector ISA. It is not. It is a packed SIMD ISA. Right? Now, IBM has SIMD support in their simulator. Gem 5, the Gem 5 mainline branch does not. Gem 5 experimental, nope. But Virginia Tech, we've had word that they have had added some VSX instructions in because they're aiming to be able to run full Power 9 binaries. Whereas for the Gem 5 experimental branch, everything was compiled with -m no AltiVec, -m no VSX for the Linux bare metal operating system thing with Buildroot. So that by the way, you can find in the Gem 5 port support package, and a thing. So Sandopan has that. I can't remember what the branch name was, but it's there. All right, so you can actually do you compile up Buildroot and thing, but you have to bear in mind that it will be compiled with -m no VSX, -m no AltiVec, and amazingly works. I ran it 2 years ago now, from scratch, from source code. Worked absolutely great, apart from that massive memory leak of 500 megabytes a second thing. So Virginia Tech are planning to add VSX. QEMU has had SIMD, packed SIMD support for forever. Dolphin PC 32-bit 15 years ago, no. Carver Tools because it's the Power ISA port is sponsored by LibreSoc. Our primary focus is on SP64 scalable vectors. We will not be adding SIMD. I've had it up to here with SIMD and just not doing it. And likewise, ISA caller doesn't have it either. Doesn't have packed SIMD either. Now, bare metal support. Bear in mind, this is the ability under your emulator to be able to run full operating systems. Okay, so the IBM simulator, yes. Gem 5 upstream, no, it will only run user space programs. Gem 5 experimental branch, yes, it will. As I just mentioned a couple of minutes ago, it will run a full build root Linux port compiled with -m, no Ultivet, -m, no VSX. The Virginia Tech one, no, I don't think it does. Although I don't know. They may have started from the Gem 5 experimental branch, but it's so old that they may have chosen to go for the mainline one. QEMU, yes, that's the whole point. Is you have full user space application emulation, including command line. I mean, it's fantastic. Many operating systems you can actually download a static binary for PowerPC or any other operating system, install the QEMU relevant QEMU package for that binary, compatible with that binary, and execute, and it will literally just execute that binary, even despite the fact it's completely foreign architecture. It's absolutely brilliant. So it will do, QEMU will do both user space and full operating system support. Dolphin PC, yes, but 32-bit only, remember. So this is the whole point of these things like Sheepshaver and Pear PC and Dolphin PC. They're full operating system emulators. They're just only 32-bit, unfortunately, but never mind. Carver Tools, no, very specifically does not do bare metal operating system. That's why it gets 5 times faster than I think. Carver Tools is very specifically designed for high performance execution of user space programs. And hilariously, Isocaller, its mere 2,500 instructions per second, does do bare metal programs because it's got an MMU. So it should come as no surprise to see that Radix MMU is likewise supported, so it corresponds to bare metal, corresponds directly with MMU. So the IBM simulator does bare metal, it's got a Radix MMU. Gem 5, the mainline branch, doesn't do bare metal and doesn't have an MMU. Gem 5 experimental branch does do bare metal, does have a Radix MMU, etc., etc. And the only exception here is Dolphin PC, which I think they probably support hash table MMUs, which are a different thing. Radix MMUs are very hierarchical tables, whereas hash table MMUs are a flat. You take a hash and use that hash, the lower bits of that hash to find the page the virtual memory page that you want. Carver Tools doesn't have an MMU, and that's why it gets the performance. Now, about that, basically, the penalty of emulating an MMU is absolutely insane. Right? When you emulate an MMU, basically any instruction, just even load the instruction, or to load any load of the load or store of data, or loading of instructions, you have to do a massive, computationally expensive lookup of the virtual memory. You have to interpret in your host operating system. You have to interpret. You have to emulate the level 1 cache. You have to emulate a level 1 cache lookups and misses. You have to do TLB lookups and TLB misses. All this is in software. It's not just in software. It's in software per load and store and per instruction loaded. I mean, it's mental. So it's horrendously costly, and is why Gem 5 drops an order of magnitude, and QEMU drop an order of magnitude compared to Carver Tools, because Carver Tools, by doing user space only, user space as far as it's concerned doesn't give a damn about virtual memory, because it's a flat ubiquitous memory space. So you just completely bypass the whole thing, whole concept of virtual memory entirely, and consequently it's way quicker. You can actually allocate guest memory to run the application. All your load stores will just, you can look, your load goes to address 50. You can look up memory at address 50, whereas on these bare metal ones, which are doing memory lookup, you have to go, oh, you want memory from address 50? Let me just look up that, see if it's first in the level on cache. No, it's not in the level on cache. Let me see if it's in what the TLB is, or whether there's a TLB entry for that thing, etc. And it can be 1,000 instructions executed per guest load, guest store, or guest instruction lookup. And IsoCaller, yes, that's what that Relix MMU.py was for. We don't even have level 1 caches, but at least we have the Relix MMU. It's horribly slow. Again, like I said, we don't care. It's for verification of whether the HDL is correct, and for bit level accuracy, and for checking that the specification has been implemented correctly. So it's very basically it. There is actually a lot behind these emulators, and a lot that you have to do and get right. It's not just sort of thing. Maybe it works, maybe it doesn't. You actually have to know about the internal details of the architecture that you're emulating, to right down to bit level. And you can't, especially with the IEEE for floating point, you can't rely on the hardware, the host hardware, having that capability that's exactly the same capability as that which you are emulating. And so consequently you end up with these order of magnitude performance hits, and that's just how it is. But you have to bear in mind that these emulators, they're extremely important. As Peter Su put it, his thing, if you're going to commit to hardware, you're looking now at sort of like a $50 million investment. Mask charges for 7 nanometer, production mask for 7 nanometer are $16 million. 4 to 5 nanometer will be $32 million for masks. 3 nanometer will be $64 million for production masks with foundries. It's completely insane, and you make one mistake that you could have avoided by committing, $50,000, and a few months' work in a simulator. You start to understand why these simulators exist, despite the fact that they are multiple orders of magnitude slower. The costs are multi orders of magnitude less, and save you from making horrendous mistakes. Plus, also, I find it fascinating for research purposes, that sort of thing. Experimenting with adding new instructions and things. So it's always great. Anyway, thank you very much. I'll leave it at that.